Welcome to the last part of the lecture on backtracking. In the previous lecture, we have seen the principle of backtracking. How does backtracking work on the state space tree and then arrives at a solution. Now, in this lecture, let's try to solve four queens problem and see how backtracking tries to find a solution for the four queens problem by evolving the state space tree. Remember, in the previous lecture, I have placed the state space tree and then shown how backtracking explores the state space tree. But actually, the state space tree is not completely constructed, it is evolved gradually. So, now in this lecture, you realize how the state space tree is gradually evolved and backtracking finds a solution by gradually evolving the state space tree. So we start at the root node. The root node represents the empty board configuration and the root node is at level 1. So the value of k is equal to 1 as we said in the previous lecture. So at root node, which is also called as the E node. So I introduced this new term E node. What does E node stand for? E node stands for the node which is being currently expanded by choosing the values of xk. The idea is very simple. E node means expanded node. Node being expanded, node under. So we consider the value of x1 equal to 1 and create a child. So this child represents the partial solution x1 equal to 1. As I said earlier, while explaining the principle of backtracking, as soon as we create a node by choosing one of the values of xk, we check whether the partial solution represented by that node satisfies the bounding function or not. We no more say constraints, we talk about bounding function because the constraints are encapsulated in the form of bounding function. All the constraints are put together and we call the complete set of constraints as one bounding function. So does it satisfy the bounding function? The bounding function form is b of x1. So trivially, b of x1 satisfies the constraints because there is only one queen. So there is no question of two queens being under attack. Now at each node, I not only try to show you the partial solution, I also try to show you the board configuration corresponding to the partial solution, the chessboard configuration corresponding to the partial solution, so that you can easily understand how you can find out the solution for 4-queen problem using backtracking. And because this node satisfies the bounding function or the partial solution represented by this node satisfies the bounding function, this node next becomes the E node. The node under consideration or the node which will be expanded and the solution is explored with this node being expanded. And as I said earlier, this is the board configuration corresponding to this node or E node which is going to be expanded. x1 equal to 1, which means the first queen is placed in the first row, obviously, in column 1. Now, this E node is at level k equal to 2. So we create the children of this E node by choosing the values of x2. The possible values, as I said earlier, are x2 equal to 1, x2 equal to 2, x2 equal to 3, x2 equal to 4. And we obviously know that some of the values are trivial. But nevertheless, let's see, for the sake of completeness, how backtracking proceeds. x2 equal to 1. So this node is a result of choosing x2 equal to 1. And what is the partial solution represented by this node? x1 comma x2. That is 1 comma 1. Does it satisfy the bounding function? P of x1 x2. It does not satisfy the bounding function. Because it does not satisfy the bounding function, the partial solution represented by this node does not satisfy the bounding function, we kill this node. This is another term that is used in backtracking. When we kill this node, what it exactly means is we are not exploring the portion of the state space tree rooted at this node. Because this node being the root, there may be state space tree which can be explored, but because this node does not satisfy the bounding function, or the partial solution represented by this node does not satisfy the bounding function, we prune this part of the state space tree and we do not explore this part of the state space tree under this node or the subtree rooted at this node. This process is called as killing. So this node is said to be killed. Because this node is killed and the solution space is pruned because of the violation of the column constraint, the board shows you that the column constraint is violated by the solution x1 equal to 1 and x2 equal to 1. We create the next child of this E node. And the next child of the E node is constructed by choosing the value of x2 equal to. And what is the partial solution now represented by this node? The partial solution that is represented by this node is 1 comma 2. That is x1 equal to 1 and x2 equal to 2. Does it satisfy the bounding function? We keep asking this question as soon as the child is created by choosing a particular value of xk. This node satisfies the bounding function or not is checked by looking at the values of x1 and x2. x1 is not equal to x2, so it satisfies the column constraint. But unfortunately, it does not satisfy the diagonal constraint because the row difference, absolute row difference is 1 and the absolute column difference is also 1. So as a result of which, we kill this node. And to make things more illustrated, have a look at the board configuration corresponding to this node. The board configuration corresponding to this node is this. And we know that the diagonal constraint is violated. So what is the next thing to be accomplished? The next thing to be accomplished is construct the child corresponding to the value of x2 equal to 3. So we create the next child of this E node by choosing the value of x2 equal to 3, and immediately we put the question, does it satisfy the bounding function? P of x1 comma x2. Does it satisfy? Let's see, x1 is not equal to x2 because 1 is not equal to 3. And the absolute row difference is 1. And the absolute column difference is 2. So it satisfies the bounding function. Because it satisfies the bounding function, this node will become the next E node, which will be explored further, which will be expanded further. So this becomes the E node. And as I said, for our illustration, this node corresponds to this board configuration, x1 equal to 1 and x2 equal to 3. The second queen is placed in the second row, obviously, in column number 3. So because this node becomes the E node, we create the children of this E node and try to expand the solution by adding the next component, that is the value of x3. x3 equal to 1. So as a result of x3 equal to 1, this node is created, and does it satisfy the bounding function? It does not satisfy the bounding function for the trivial reason that x1 equal to x3 and hence column constraint is not satisfied. So what is the next thing that is accomplished? The next thing that is accomplished is killing this node. We don't further explore this node or explore the state space tree rooted at this node. So the next step is to create the next child by choosing the value of x3 equal to 2. Of course, before that, you can have a look at why this node representing the solution x1, x2, x3 as 1, 3, 1 violates the bounding function because the column constraint. So let's move on to the next step. The next step is x3 equal to 2. So does it satisfy the bounding function? Of course, this already satisfies the bounding function, so the pair x1 and x2 satisfy the constraints. Let's look at the pair x1 and x3. x1 is not equal to x3, so the column constraint is satisfied. And the diagonal constraint, the absolute row difference is 3 and 1 is 2. The column difference is 2 and 1. So it satisfies the diagonal constraint as far as the pair x1 and x3 is concerned. But of course, we also have to check the pair x2 and x3. Let's look at x2 and x3. x2 is not equal to x3, so the column constraint is satisfied. Now let's look at the diagonal constraint. The row difference is 1 and the column difference is also 1. So the partial solution represented by this node does not satisfy the bounding function, hence this node is hit. You can have a look at the board configuration, why the bounding function is not satisfied. The bounding function is not satisfied because the diagonal constraint is violated between the queen 2 and, as we have said, that x2 and x3 do not satisfy the column constraint, the diagonal constraint. Of course, because you are used to now the principle of backtracking, I at once created the nodes corresponding to the value of x3 equal to 3 and x3 equal to 4, and also have shown as nodes which are killed because the partial solutions represented by these two nodes do not satisfy the bounding function. If you want to have a board configuration view, you can see that x3 equal to 3 violates the bounding function because these two queens are in the same column. And this node representing the solution 1, 3, 4, 1, 3, 4 also violates the constraint because x2 and x3 have a row difference of 1 and the values x2 and x3, 3 and 4 also have a column difference of 1. So the diagonal constraint is not satisfied and hence the bounding function is not satisfied at this node. So this node is killed. Now what should be our next step? Because all the children of this E node, the node being expanded, are explored, and we found that none of them satisfy the bounding function. Because none of them satisfy the bounding function at level k equal to 3, because we have explored all the possible values of xk, that is x3, the algorithm backtracks and makes this node as the E node, the node to be expanded, and tries to build its children which are unexplored. Can we find out what is the unexplored child of this node? The unexplored child of this node is the one corresponding to the value x2 equal to 4. So backtracking in the next step builds or creates the child of this E node by choosing the value of x2 equal to 4. But once again, does it satisfy the bounding function? x1 is not equal to x2. The row difference is 1. The column difference is 3. So it satisfies the bounding function. Hence, this node becomes the E node. This tells you the board configuration and how the partial solution represented by the node satisfies the bounding function. Because this satisfies the E node, we try to create the children of this E node, which is at level 3, by choosing all possible values of x3. But however, x3 equal to 1 does not satisfy the bounding function. By this time, you should have been well aware why bounding function is not satisfied by this node, and hence this node is killed. And we look at x3 equal to 2. Does it satisfy the bounding function? Like b of x1, x2, x3 is b of 1, 4, 2. We find that this node satisfies the bounding function because x1, x2 have already satisfied the constraints, x1 and x3 also satisfy the constraints, and finally x2 and x3 also satisfy the constraints. So backtracking makes this node as the E node and then explores the solution further by constructing the children of this node by choosing different possible values of x4. Unfortunately, none of the values of x4 and the resulting children satisfy the bounding function, and hence all the nodes are killed. Let us see the same thing in a more illustrated way. This represents the board configuration corresponding to this E node, x1 equal to 1, x2 equal to 4, and x3 equal to 2. And now we have 4 children that are constructed corresponding to x4 equal to 1, violates the bounding function, x4 equal to 2, violates the bounding function, x4 equal to 3, violates the bounding function, and x4 equal to 4 violates the bounding. So we see that all the possible values of x4 are exhausted. So backtracks to the previous level, that is k equal to 3, and looks at other unexplored values of x3. What are the other unexplored values of x3? Other unexplored values of x3 are 3 and 4, because we have already explored the possibilities of x3 equal to 1 and x3 equal to 2. So we go back and look at the possible values of x3 equal to 3 and x3 equal to 4, and we find that the resulting children will not satisfy the bounding function, and hence these nodes also will be killed. Let us see more illustratedly with the help of the board configuration. x3 equal to 3 violets, x3 equal to 4 violets. So now, what is the next thing that is accomplished? We see that at this E node, we have exhausted all the possible values of x3. So the backtracking algorithm backtracks to the previous level and looks at the other possible values at this level, that is, other possible values of x2. But we have already exhausted all the possible values of x2 as well. So backtracking algorithm backtracks to the previous level once again and looks at other possible values at this level. This level is k equal to 1, and we have already explored the possible value of x1 equal to 1, and hence the next value that will be explored will be x1 equal to 2. So we look at x1 equal to 2, explore this node, create this node. This becomes the next E node if it satisfies the bounding function. Let's see whether it satisfies the bounding function or not. It satisfies the bounding function trivially because x1 equal to 2, there is only one queen. And once it becomes the E node, we construct the children by choosing the values of x2 equal to 1, x2 equal to 2, x2 equal to 3, and x2 equal to 4. And we find that the children resulting from x2 equal to 1, x2 equal to 2, x2 equal to 3, and the partial solutions represented by them violate the bounding function. So we finally arrive at x2 equal to 4. This can be seen in terms of board configuration, how x2 equal to 1, 2, 3 violate the bounding function. So finally we settle down for x2 equal to 4, and the partial solution represented by this node x1 comma x2 satisfies the bounding function. So because it satisfies the bounding function, this becomes the E node. So once it becomes the E node, we start building its children and explore the partial solutions represented by its children. So x3 equal to 1 is the child that is created for this E node, and does it satisfy the bounding function? It satisfies the bounding function. Because it satisfies the bounding function as shown by the board configuration, this node becomes the next E node, and we build its children by choosing the values of x4. But unfortunately, x4 equal to 1 and x4 equal to 2 violate the bounding function as shown in this diagram. x4 equal to 1, x4 equal to 2. So we choose value of x4 equal to 3, and this is the node that's created, which represents the partial solution x1 equal to 2, x2 equal to 4, x3 equal to 1, and x4 equal to 3. And because this satisfies the bounding function, it becomes the next E node. But however, this E node is at level 5. This is at level 1, this is at level 2, this is at level 3, this is at level 4, and this is at level 5. And the 4-queen problem requires the children to be constructed only for n plus 1 levels. So hence, this node becomes the answer node. This E node, because is at level 5, which is equal to n plus 1 for 4-queen problem, automatically becomes the answer node. And this is where we claim that we found a solution. And the solution is represented by the 4 tuple 2, 4, 1. Now, should we stop here? The answer depends on what you want to do in solving the four queens problem. Suppose you are interested only in one of the solutions, then because you found out the solution represented by the tuple 2, 4, 1, 3 that satisfies the constraint stated by the problem, you can stop here. But if you want to find out all possible solutions, then you have to continue the search for the solution by following the principles of backtracking. For example, if you want to continue, the next thing you would do is go back to the previous level, because at this level, all the possible values of x4 are exhausted. So from this level, we go back to the previous level and then look at the other possible options of exploring with x3 equal to 2, x3 equal to 3, and x3 equal to 4. After you explore the solution space corresponding to these values of x3, you backtrack to this level, but at this level, all the values of x2 have been exhausted. So you further backtrack to this level and explore the subtrees of the state space tree corresponding to x1 equal to 3 and x1 equal to 4. And after completing exploring the state space tree corresponding to all the values of x1, x1 equal to 3 and x1 equal to 4, you can stop, because by that time you might have found out all the solutions that possibly exist for the given four queen problem. So I encourage you to continue construction of the state space tree and application of the backtracking algorithm to find out other solutions of the problem. And also I encourage you, after doing that, you build the whole of this state space tree on your own, starting from the root node, and practice it once again so that you get well acquainted with backtracking and solving the four queen problem. In fact, it's a generalization of an n queen problem using backtracking. Now let's look at some more terminology associated with backtracking. These terms should be clear and obvious because you have already seen how backtracking works in solving four queen problem. All paths from the root node to the leaf nodes define the state space tree of the problem. This is the complete state space tree. Once again, I would like to tell you that the whole of the state space tree is not constructed in backtracking. The state space tree is evolved, and as and when a particular node fails in satisfying the bounding function, we stop there and explore other possibilities of the values of the variable at that level, or if all the possible values at that level are exhausted, it backtracks. Solution states are those problem states which from the root node to that node defines a tuple that satisfies the explicit constraints in the solution space. I repeat, solution states are those problem states, yes, whose path from the root node to S define a tuple that satisfies the explicit constraints. In this state space tree, you find that the leaf nodes are the solution states. It's not necessary that in all the state space trees, the leaf nodes only should become the solution states. In this configuration of four queens problem, it so happens that the leaf nodes represent the solution states because the solution represented by the leaf node satisfies the explicit constraints. The solution is an n tuple or a four tuple in case of a four queen problem, which should give the values for x1, x2, x3, x4. So it's only the leaf node that will have the values for all the four variables x1, x2, x3 and x4, and hence they qualify to be the solution states. Now, answer states are those solution states that satisfy the implicit constraints. What are the implicit constraints in the four queen problem? The four queen problem, or for that matter in the n queen problem, the implicit constraint says that no two queens should attack each other, and we find that node number 31 satisfies the explicit constraints because it gives values for x1, x2, x3, x4, and also satisfies the implicit constraints, a solution which we found previously. And you will find that the node number 39 defined by the values of x1 equal to 3, x2 equal to 1, x3 equal to 4 and x4 equal to 2 also satisfies the implicit constraints, and hence this solution node is also called as answer node. So answer node or answer states are those solution states which satisfy the implicit constraints. Solution states or solution nodes are those states or nodes which satisfy the implicit constraints. Let's try to identify what's meant by a live node. A node which has been generated and all of whose children have not yet been generated is called as a live node. Let us take the snapshot of the backtracking problem which we have solved previously. This is one snapshot of the problem where we have created the node corresponding to x3 equal to 1 and killed that node. At this point of time, we see that this is the node that is being expanded, and this node is called as the E node. Now, the node is to be explored by constructing other children corresponding to the values of x3 equal to 2, x3 equal to 3 and x3 equal to 4. Hence, this is also a live node because a live node is a node which has been generated and whose children are yet to be generated. Similarly, this is also a live node at this point of time because there is one more child pending to be created corresponding to the value of x2 equal to 4. This is also a live node because the children corresponding to the values x1 equal to 2, x2 equal to 3 and x3 equal to 4 are yet to be generated. And we also see from the backtracking procedure that one of the live nodes will be the E node. That node which is being currently expanded, that live node which is being currently expanded is called as the E node. That's what we precisely see in this definition. The live node whose children are currently being expanded or currently being generated is called as the E node. And I repeat, live nodes are those nodes whose children are yet to be generated. E node is a live node, one of the live nodes whose children are currently being generated or which is being currently expanded. A dead node is a generated node which is not to be further expanded because it does not satisfy the bounding function, or it can also be a node whose children have been completely generated. For example, these two nodes are dead nodes because they violate the bounding function. These nodes are also the dead nodes because they also fail to satisfy the bounding function. This node is also a dead node in this snapshot of the solution because all the children of this node have been generated. Hence, this is also called as a dead node. So, a dead node comes in two flavors. One is a node which should not be further explored because it does not satisfy the bounding function, or a node all of whose children have been already generated. So in backtracking, as you have seen, a list of live nodes are present, and one of the live nodes is the E node. As soon as a child of the E node is generated, the child becomes the current E node only if it satisfies the bounding function. If an E node does not satisfy the bounding function, the E node is killed. This corresponds to the depth first generation of nodes. If an E node is killed, the next child of the parent is generated, and the next child generated becomes the E node. That's what you have witnessed in the solution of 4-queen problem using backtracking. If all the children are explored at a level, then the algorithm backtracks to the nearest ancestor live node whose children can be generated next. And finally, we conclude by saying that the state space tree is not constructed physically, though it has been shown as if we are constructing the state space tree, even partially. Physical construction of the state space tree is not done. The execution flow of the algorithm mimics the logical construction of the state space tree, but it is never constructed physically. A for loop normally iterates through the nodes at each level of the tree, and a recursive call in the for loop descends down the tree at each node. Let's look at the outline of the algorithm. N-queens function. Let us assume that X is an array with indices 1 to n, and let us assume that this array X is global. The function N-queens takes one parameter, which is the row. Actually, this row stands for the level, and initially N-queens is called with row equal to 1 or level equal to 1, because we said the backtracking algorithm begins at the root node, which is at level k equal to 1. So row or level, both the words are synonymous. So you can treat row as level, and N-queens function is invoked with level value or row value equal to 1. Now, at each level, we find that we explore all possible values of xi. They are nothing but all possible values of columns. In 4-queen problem, n equal to 4, and xi becomes 1, xi becomes 2, xi becomes 3, and xi becomes 4. And xi is nothing but the column value, as we said in the previous explanation of the solution of the 4-queen problem. So for a particular level, for a particular column value, we check whether the values so far existing in the partial solution, x1, x2, x3, or x row up to level row, is feasible or not. If it is feasible and if it satisfies the bounding function, then we check whether we have reached the last level. If you have reached the last level, then you have found out the solution and you print the solution. And if you haven't reached, then that node which is created becomes the E node, and we invoke N-queens at the next level, that is level plus 1 or row plus 1. So this is just an outline of an N-queens algorithm, and you can always try by implementing this function, and this function is called with the parameter value of row or level as 1. Thank you.